Hello and welcome back to Worked Heat Transfers Examples. This time we're going to work on a problem that talks about a Hotwire Anemometer. These devices measure fluid velocity. The working principle is based on the fact that the heat transfer coefficient changes with the velocity of the fluid that moves over the hot wire. The hot wire situation we're going to look at here operates with these parameters. There's air flowing over a hot wire. We know that the temperature of the air is 25 degrees Celsius, but we don't know the velocity. We know the diameter of the Hotwire anemometer. We know that its surface temperature is 40 degrees Celsius. And we know that the heat per unit length of this wire, which is a cylindrical pillar, is 35 watts per meter. We are asked to find the free stream velocity of the air moving over the hot wire. We will make the following assumptions. First, we assume that the cylinder is isothermal. Anemometers can be set up so that they have a constant temperature where the current running through the wire changes to maintain that temperature, or they can have a constant heat flux where the current running through the wire is constant. We'll assume that the fluid and material properties are constant. We'll assume that the convection heat transfer is much greater than radiation from the surface of the wire. We will also assume that the problem is at steady state. And at steady state, that means that the heat per unit length running through the wire, or between the wire and the fluid, is constant. We're going to try to use our convection flowchart here, but at the risk of spoiling things, we'll see that the flowchart doesn't exactly work in this problem, and we'll have to learn to be a little bit flexible. But we will start by understanding the geometry and boundary conditions of our problem. Again, we have external flow over an isothermal cylinder. We saw last time that there are different Nusselt number correlations that we can use. Here's one, but I didn't like this one last time because it's a little harder to put into my calculator. We'll skip it again. Here's the one we used for example 2. I'm going to suggest that we use this one again, but in the worked written solutions that are found on the My Courses website, you'll see that there's other appropriate Nusselt number correlations. And the answer we get depends on the correlation that we choose. So what that means is that all of these answers, all of these solutions are just giving us an approximation or a model of the real system. To understand how the system would actually perform, we'd probably want to run an experiment. So I'm going to use this Nusselt number correlation because it's fairly straightforward and we've used it before. The problem here is that we don't know what the Reynolds number is, so we're not sure what C or M are. The good news is the Reynolds number ranges on table 7.2 are pretty wide. So I'm going to make the assumption that we're going to have a Reynolds number between 4 and 4,000. We'll check that out later. The next thing we want to do is determine relevant properties at an appropriate temperature. Again, the temperature we'll use is the average temperature between the surface and the free stream. In this case, that temperature is 32.5 degrees, or 305.5 degrees Kelvin. If we look at table A.4 for properties of air, we can see that the temperature ranges are pretty far apart here, which means that the fluid properties in air are a weak function of temperature. So I'm going to say that 305.5 is just about the same as 300 to save myself a little bit of linear interpolation. I'll pull the numbers off the table and I'll find viscosity, thermal conductivity, and Prandtl number. Now, what my flowchart tells me to do next is to calculate the Reynolds number. The problem is we can't do that because we don't know the velocity yet. So you might get to a part like this in a problem and feel a little bit stuck. I think when we feel stuck, it's good to look at the information that we do have. And this flowchart is set up to find the heat transfer, or in this case, the heat transfer per unit length. But thankfully, in this problem, we're given the heat transfer per unit length. So we'll try to skip step 3, eventually use our understanding of the heat transfer per unit length, and hopefully find a way to use that to get back to finding the free stream velocity. So we'll skip 3 for now, and we'll go to this appropriate convection correlation. Now, I've talked about this already a little bit in this video, but I want to use this average Nusselt number correlation, even though there's probably other correlations that would also be acceptable. I'll assume, or guess, that my Reynolds number falls in this range between 40 and 4,000. I'll have to check this assumption later. But now, from table 7.2, I can find a guess, or a first guess, for C and M. Now, instead of solving for H and finding Q, I'm going to use Q prime to find H. So I'm given in the problem that the heat per unit length on my wire is 35 watts per meter. I know the equation for Q prime is Q divided by H, or the height of my wire. Q is equal to HA times delta T. A is the perimeter multiplied by the height. And when I put this in, I see that the heights cancel out, which is nice because I don't know the height or the length of my wire. So now I have an equation for Q prime. I can rearrange to solve for H. I put some numbers into my calculator, and I find that the heat transfer coefficient in this problem is fairly high at 1,485 watts per meter Kelvin. So now I want to use the heat transfer coefficient to find an average Nusselt number. I have to remember that the Nusselt number for this cylindrical pillar is based on the diameter of the wire. I know all of these numbers, so I can put them into my calculator, do a little bit of math, and find that the average Nusselt number is 28.6. Now, I'm going to use my Nusselt number correlation to go from Nusselt number to Reynolds number. I had looked up values of C and M on the table previously, so I have a correlation that I'm going to use for the Nusselt number. I can rearrange this equation to find an expression for Reynolds number to the power of 0.466. Then I can do a little bit more algebra and find that my Reynolds number, which again is going to be based on the diameter of the wire, is 3,074.1. Remember, this is a dimensionless number. Here, I can see that the assumption that I made before, that Reynolds number would fall between 40 and 40,000, ends up being correct. If it wasn't, I would have to iterate through this problem and pick a different guess for my Reynolds number range. But in this case, my assumption is shown to be reasonable. Now I know my Reynolds number, and I know that the Reynolds number is a function of the free stream velocity. So I can get an equation for my free stream velocity. I know all of these values, and I can put them into my calculator to find that my velocity in the free stream is just over 123 meters per second. Now again, in the handwritten solutions for this problem that can be found on the My Courses website, you can see that choosing a different Nusselt number correlation can give you a different velocity. So it's important to remember that all of these calculations are approximations and that there's some uncertainty involved in all of this modeling. Our celebratory image is brought to us this time by my middle daughter, Emily Schertzer, who wants you to know that now you have knowledge of the heat transfer. Thank you, and I'll see you next time.